Welcome. In this video, let's talk about the binary number system. To easily understand the binary system, we compare with the decimal system. So in that way, we can easily understand what the binary system it is. First, look at the decimal digit. For the decimal system, we have 10 symbols. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. This is 10 digits. Compared with binary digit, we only have two symbols, 1 and 0. This is an example for a decimal integer. For example, we have a decimal integer, 111. This notation means here this number is the decimal number. How to interpret this 111? Let's look at last digit. The last position, last digit is actually 1 multiple tens power 0. So that is any number power 0, that is 1. So that is 1. The second digit, that is tens position. In this tens position, we have number 1 and then multiple tens powers 1. So this is the 10. In the third position, that is our hundredth position. So the hundredth position is 1 multiple tens power. This is 100. So 111 is going to add together 100 plus 10 plus 1. So that is 100 plus 10 plus 1 is equal to 111. This is base 10 number. So we read this one. We know, okay, this is 100, this is 10, this is 1. Then compare with binary integer. For example, binary 0, this number 2 is just a notation to indicate this is base 2 number. Okay, binary digit 0 is actually equal to 0 multiple 2's power 0. So any number power 0 is going to 1. 0 multiple 1 is going to be 0. So the binary digit 0 exactly equal to decimal digit 0. This 10 indicate this is base 10 number. So the here has a 0, 0. We use this notation to tell what is the number system. Okay, the same thing. Binary digit 1 is equal to 1 multiple 2's power 0. So that is 2's power 0 is 1. 1 multiple 1 is 1. So its binary digit 1 is exactly equal to the decimal digit 1. Let's continue. Within the binary digit 1, 0. Okay, since the binary only has 1 and 0, if we over 1, we have to use another position to represent the different number. So in the binary digit 1, 0 is equal to 1 multiple 2's power 1 plus 0. You see here, 0 multiple 2's power 0. That is 1 multiple 2 is equal to 2. So the plus 0, 0 multiple 2's power 0, that is 0. So 2 plus 0 is equal to 2. So this is decimal digit number 2 is going to equal to binary number 1, 0. Okay? Another example. 1, 1 in the binary number. In the binary number 1, that is the first one in the right, the first one in the right is going to be 1 multiple 2's power 0. This is going to be 1. 1 multiple 1 is going to be 1. The second position is 1. So that is 1 multiple 2's power 1 is going to be 1 multiple 2 is going to be 2. So 2 plus 1 equal to 3. So in the binary digit 1, 1, it's going to be equal to decimal digit 3. So did you find the rules as here is exactly the same as our decimal. The first position is going to be the individual numbers. The second position is going to be tens. The third position is going to be hundreds. So that is always 10 power to this position number. 0, 1, 2. This is 0, 1, 2. And same thing in the binary digit is always 2's power based on his position number. Okay, so here 0 going to be 0 multiple 2's power 0. 0 multiple anything is 0. And the second position is here. What we use the number 1 as position. We count from 0, 1, 2 in that way. So here, this is 2's power 1 multiple 0 is going to be 0. And then the 1 is going to be the 2's power 2 multiple 1, that is going to be 4. So 4 plus 0 plus 0 is going to be 4. So 1, 0, 0 in the binary is going to be the decimal number 4. So in another way is the decimal number 4 going to be represented into 1, 0, 0 in decimal. Okay, you just match here position 0, 1, 2. Decimal is going to use 10's power. The binary goes to use 2's power. And then based on their position to give the 2's power number to convert it to the decimal. Okay, there is another very important concept. It's called most significant and least significant digit. The leftmost digit, the leftmost digit is referred as the most significant digit or bit. So the leftmost, this is the highest number. For example, here the position is going to count from the right to left. This is 1, 2, 3, 4, 5, 8. The position here is going to use most significant bit. The rightmost, this is the rightmost. The rightmost is referred to least significant digit or bit. So we call this one is least significant bit. During the binary calculation, we use this concept a lot. In this slide, let's look into the position number system. Let's compare with decimal and the binary. For example, if we have a number, decimal number, 442.256, and then let's mark the position. Before the decimal point, the first digit is 1. The second digit position is 2, 3, 4, 5. In this way counted. After digit, we are going to mark as -1, -2, -3, -4, so on and so forth. And each position has different weight. In the decimal system, we know the first position, that is individual number. The second position going to be the tens position. The third position going to be the hundredth position. So that is tens power 2. The fourth position, that's going to be the thousandth position. So that is going to tens power 3. You see, this is position number. The power is going to be -1. So in the position 1, we use the 0. So 0 power, 10 power 0, that is individual number here. This is tens position, hundredth position, thousandth position, and the after decimal position is going to be the ones, tens, hundreds, thousands. It's just in the fraction is minus. Okay, so the decimal number 442.256 is going to be the individual, the first position before the decimal point is 2 multiple tens power 0, and then the 4 going to be multiple tens power 1. The third position 4 is going to be 4 multiple tens power 2, and since here has no numbers, that is 0 multiple anything is going to be 0. So the before the decimal point, we know that is 442. After decimal point, it's going to be 2 over 10, 5 over 100, 6 over 1000. So interpreted to represent the decimal number going to be 442.256. This is our daily use, so we easily understand. Same thing. In the binary, we also can be compared with the decimal. Just the different way is weight. The decimal point is weight and tens power. The binary number is just 2's power. You see here, this is decimal point. The first position, second, third, fourth, and then the weight going to 2's power 0, 2's power 1, 2's power 2, 2's power 3. That is going to be the weight. It's the same thing. After decimal, it's going to 2's power -1, 2's power -2, 2's power -3. For example, if we have a binary 1001, point 101, what is this number to translate into decimal? Okay, here we are going to first digit multiple 2's power 0, second digit multiple 2's power 1, third digit multiple 2's power 2, fourth digit multiple 2's power 3. Okay, and 1 multiple 2's power 3 is 8. Let's see, 2 multiple 2 and multiple 2. So 2 multiple 2 is 4, and then multiple another 2 is 8. So in this position, this one represents 8. This position is 0, is nothing. 0 multiple anything is 0. The 0 is just write down, and this is 1, write down here, since 2's power 0 is 1. So it is 8001. So before the decimal, we are going to have 8 plus 0 plus 0 plus 1. That's going to be 9. Okay, and after decimal point, 1 multiple 2's power -1 is actually 1 over 2. 2's power -2 is going to 0 over for anything 0 multiple anything is going to be 0. The here 2 to the power 3 going to be 8, but it is negative, so we put underneath this bar, so it's 1 over 8. Here 0 is going to be 0. And then 1 over 8 is to be the 0.125, and this is a 0. The first one is 1/2 is 0.5. So 0.5 plus 0 plus 0.125, that's going to be 625. So the decimal number for this binary representation is going to be 9.625. Okay, this is the position system. No matter how long the binary digit is going to be always 1 and 0. So you put it in the string and begin to count from the least significant bit, and then you are going to know, then add together, you're going to know what is exactly equal to the decimal point. This is example compare binary and decimal numbers. So the position is very important. When we understand the position, 2 to the power position number -1, and then we are going to know how to calculate the decimal numbers. Okay, I'm stopped at here. Thank you very much. See you next time.